So I was saying that everybody is eager for more science, as Thomas was saying. Nobody wants to go for a coffee or wrap it up. So let's stay here a little bit longer. Yes, the hallmarks of cancer. And Thomas did a great job on Monday in wrapping things up. And for that reason, what I am going to do is, in effect, address some of the hallmarks of cancer as they have been appearing in my life and in my work. Whenever I give this type of lectures, I always motivate myself once again by the data. And the data is clear. The data is clear. 2020, before COVID, 10 million deaths were attributed to cancer globally. And I like, as I said, to motivate myself by comparing with what was happening that year. That year in 2020, 2019, 2020, 138 million births in that particular year. When it comes to deaths, overall, globally in 2020, it was 60 million. So in 2020, 1 out of 6 of all the people that died because of cancer. Okay. This is a grim realization. And this grim realization comes with the fact that we still have not solved the problem of cancer, which we know that dates back really in time. First evidence of cancer cells, 70 million years ago. First evidence of cancer cells in humans, 3,000 years ago. First evidence of surgery in cancer, more or less 3,000 years ago. It is very nice. A papyrus has been retrieved from the 2,600 something BCE, where the surgeon concludes there is no treatment for cancer, or what they identify as cancer. Okay. These grim realizations, of course, are the ones that drive the development and the need to have the hallmarks of cancer, to try to understand, in effect, what are the most important components that drive cancer, and in effect, help the scientific community organize their research and solve it. But a problem that old, 5,000 years old, necessitates much more knowledge and effort than simply the medical science or the biology. This is why we are here. This is why mathematics have been drawn into this big problem, because it is yet to be solved. Not only that, but as year goes by, we realize that more and more hallmarks of cancer need to be tackled before we conclude, hopefully, to a solution. We all rely, as a mathematical oncology, if you want, field, on the papers by Hanahan, Weinberg, 2000, 2011. We have heard so many things about that this time. And very recently, the paper by Hanahan, the 22 paper on the hallmarks of cancer, which again highlights for me that our efforts to understand and solve the problem, somehow there is something that eludes us. Question, is this just in oncology, or is this also a problem of mathematical oncology? Has mathematical oncology been able to capture the number of cancer? My answer is no, not yet, at least, right? And my effort today will be to focus in one of the hallmarks of cancer invasion, and if you want, the subsequent metastasis, and briefly take you through the first stages of development about that. In any case, I want to motivate myself. This is an in vitro assay of cancer cells invading in the tissue. So what you see here is in time, initially, later, and much later, cancer cells invade in the tissue, right? I don't want to come to much detail about that, but I want to draw your attention in this particular case. This is the liver of a human patient where cancer islands appear in the tissue in this light yellowish color. And if you do a little bit of mathematics, you realize that these are disconnected topological, if you want, components within the tissue, which makes you think how they have been formed from one to the other. What do we see here in effect? And what I argue here is that we see an evolution, if you want, in this particular tissue, time evolution in this particular tissue of so-called cancer islands that grow and merge with each other. So in effect, what I'm saying is that what among the many problems that we have to solve and understand is to be able to reproduce mathematically this type of phenomenon. Cancer islands appearing in the tissue that later on they grow and they merge, right? I will come to mice at the end of my talk, but first somehow for comparison, healthy, if you want, tissue and cancerous lungs with a number of, it's not very visible, I think, a number of micro and larger metastases in the tissue. So my objective today is to take you through the number of models that they have been used, and some of which we have addressed in this week. They have been used in order to be able to describe mathematically this type of processes. And for that, I will first go to classical models and spheroid models. Spheroid models, and of course, it's something that we all know. These are tumor spheroids as they have been developed in Petri dishes, but mathematically, they have been studied from the past. And one of the first papers that I like is by Anna Laird in '64, where what they do in effect in this paper, what the author does in this paper is to study, if you want, growth curves, identify growth curves for cancer in particular cases. The author, in this case, concludes, and maybe I might even jump to the conclusion, concludes to the double exponential, right? The Gompertz, the one that we have seen so many times appearing in plants, in tissues, in many different things. In their study, in this particular study, it is the Gompertz that they advocate for. Fine. So one would argue the following: can your model produce that in some sense, right? And this is the story of, this is the story behind the tumor spheroid modeling, for that matter, right? And the tumor spheroid, for that matter, modeling can be organized by the original von Bertalanffy equations that they have been used, as I said before, in a number of cases. This is the umbrella that accounts for almost all proliferation attempts that we have seen in the literature, right? So we started this week. No, we didn't start with this one. We started with the next one. A special case of the von Bertalanffy is the 2/3 exponent. It is the 2/3 exponent for the positive term, the alpha n in the power of lambda, and first power for the n, where n describes, if you want, the volume, the size, the number of cancer cells in the tumor. So you have, in effect, a tumor that grows with a volume n, and here the growth of the tumor is proportional to primarily n to the power 2/3, which makes sense because the surface of a sphere is exactly that. So that is one connection, if you want, with other modeling attempts in biology, right? In our case, a special case of von Bertalanffy with lambda 1 and 2 is what leads to the logistic equation, which is the one that it is primarily employed in our field. So we understand it, we solve it, we use it. The carrying capacity here I will address that even later in my talk. It has been the carrying capacity K here, it has been the point of research for many years. Yes, please, Patrick. Because of the ratio of the area and the volume? Yes, of the sphere. And this works very nicely even with other organisms. So, for example, this is what developmental biologists look into when you discuss, for example, the growth of a mammal like us, which we are very much close to a sphere, much closer than plants. So you can distinguish, if you want, animals from plants by the exponent that you see here. But this is where it was employed. In our case, tumor spheroid, of course, it is the surface of the sphere, 2/3 power over the volume, right? Okay, now, as I was saying, K is a place of intensive research, even in, as we were discussing this week's anti-angiogenesis drugs. The effect that they have is to decrease the K, but what I want to draw your attention to is that this K has been a point of controversy, the meaning of that, when it comes to the classical cancer growth models that we have seen. Okay, let me continue a bit more. If you change now your exponents, right, make a different choice in the von Bertalanffy, and you do some algebra here, manipulate things, right? It's kind of straightforward exercise, and take the limit at the end as lambda goes to 1, you obtain, right, the Gompertz equation, which if you solve gives rise to the double exponential, right? So somehow all the if you want proliferation terms that we typically use in our field, they can be under the umbrella of the von Bertalanffy case, right? I find this case particularly interesting because this is kind of an entropy-like approach that we use in statistical physics in other places, right? And at least for me, it is yet not understood what is the biological significance of this entropy approach. How come this double exponential, the entropy solution, in effect, is so important in physics and in biology in a similar fashion? Nevertheless, my point that I will make 3-4 times is that we are done, we are set. Mathematical oncology is over. We have developed equations that describe tumor spheroids as they grow. We can close the shop, we can do something different, switch field of research. The answer is, of course, no, and we know that already. Why? Because there is redundancy in this biological system. We do know that when the tumors grow, they stop growing as, if you want, uniform solid spheroids, they develop necrotic cores. In effect, what happens is that, as we very well know, a part of the cells inside the tumor spheroid, they starve, they die out, because they survive due to diffusion-driven processes like supply of oxygen and nutrients through the surface of the spheroid to the internal cells. As the nutrients penetrate the tumor, the nutrients get consumed, and eventually the cells deep down, they starve out. Okay, so what we did mathematically before, it is still relevant, but not enough, right? What we notice, though, experimentally at this point, is that the growth of the tumor continues with the necrotic and possibly quiescent zones, and even more, if you wish, subcomponents, grows and exhibits a very interesting equilibrium where the thickness of the proliferating zone, i.e. the thickness, the part of the tumor where the cancer cells still proliferate and grow, remains the same. So the tumor grows, but the thickness of the proliferating cells remain the same. And that was another milestone, if you want, in the development of our models. Can our models predict that now? Because we did that one before. Yes, there have been very nice works on this point, right? And this brings us to what we were discussing a little bit earlier at this case, where you say, okay, wait a minute, I do realize that there is a necrotic core. I described by R, if you want, the radius of the by R, the size of the tumor, if you want, and R tumor is the maximum size of it is the actual size of the tumor, and somewhere between, there is a distinction between necrotic and...
Because we've jumped into spatial modeling, right?
No, not yet.
Not yet? Okay.
Not yet.
I was going to ask, yeah, so...
Not yet, not yet.
Do you have a compartment approach for proliferating necrotic and quiescent cells?
Yes, there is. Yes, there is, and it stems from this description. So What one describes, and maybe I should describe that in a little bit more detail. What in effect you describe is the following: the resources C that are responsible for the feeding of the cancer cells, right? And you can think that they diffuse, right? So oxygen, for example, can diffuse inside the necrotic core, and possibly it gets consumed in the proliferating part of the outer zone, right? And this is, of course, one of the possible ways to identify, to discuss that. And
Sorry,
no,
I thought you said that theory can prove that we get in some limit, we get this constant thickness. But
experiments.
here you're right,
Yeah.
but I thought you said mathematical models can also predict.
Yes.
But in this mathematical model, I thought our neck and our tumor are constants.
No.
Oh, okay.
What in effect, and I jump to the conclusion, is that identify the interface between the necrotic and the proliferating zone, right? Right, so that the proliferating outer ring, if you want, of the tumor remains constant. I, in effect, solve the free boundary problem, where the free boundary is the boundary between the proliferating and the necrotic part. Does that answer your question?
So, but presumably this would happen only asymptotically in some sense, right?
Well, you can asymptotically, it happens, I agree, but you can identify the time where 99% of the somehow you can solve the problem very nicely as soon as you write that in spherical coordinates, in which case, of course, it means that you need, as we were saying before, to rewrite the diffusion the diffusion operator delta in spherical coordinates.
Yeah, the part that confuses me is that I would thought that both changes the function of time.
Initially, yes,
Right.
excellent.
But here is a static problem. It's an identification within a static data.
Yeah, they depend on time. Eduardo, they depend on time.
Oh,
What remains constant or close to constant is the difference of these two, R2 minus R nec. So what you can prove here with simple calculations, if you want, it is just one page of calculations. What you can prove is that these two radii, if you want, the necrotic radius, right, versus against the tumor, the radius of the tumor, the difference of the two remains constant later on. It reaches an asymptotic value.
But that actually is not what we found in the emergence from models, is that it will be very nearly constant, but decreasing over time, because
Yes.
you're feeding from a larger curvature when it's small.
Yes.
So the amount of boundary feeding one chunk of interior is larger, you get farther penetration for the small curvature tumors.
Yeah.
But it does start to approach something looking almost constant, bigger
Yeah.
than gets, but never.
I agree.
gets.
I agree. And that would have been on one of my comments. At this point, of course, this model has been quite successful in predicting the constancy, but it is almost constant
Right.
in practice. Whereas in effect, the mathematical model exhibits an asymptotic convergence towards a constant difference of the two radii
Right.
of the cells.
And you'll see that when you plot out viable rim, say,
Yes.
doing signal, like
Yes.
image analysis on, in the H model, for example. You'll see that steadily decreasing viable rim size, but it does get more and more constant.
Yes, yes. And one good question is that, for that point, the model that one has opted here for the diffusion of the nutrient or resources in the tumor microenvironment, for that matter, is not precise. This is what should be improved before redoing the calculations. So it is not simple diffusion as we have here. It might be something more complicated. Yeah, in this.
So the other thing we found a long time ago was
Mhm.
when you use just the instantaneous contour of substrate to define your necrotic core boundary,
Mhm.
if you actually started tracking necrotic cells, then what would happen was that discontinuous uptake term. So these cells now became necrotic, so you turned off the source, now the gradient popped up, and if you use these instantaneous things, those necrotic cells would come back to life without a separate.
Yes, because they are not necrotic. A better description, if you want, of the problem is closer to that on the right, that you have a multi-zonal approach where, among others, you have a quiescence part, in which quiescence part of the cells can pretend to be dead and awake again.
That only delays the problem. But yeah, you'd have
You have
high
both of them.
uptake, medium uptake, low uptake, but still, you would still have where you just barely dipped below the value, then you turn the consumption term up and it pops back up above the threshold the next few times until it dips back down again. So you
Mhm.
reduce the effect by having zonation, but you needed to have non-zero uptake, or say oxygen reaction or something.
Yes, yes, what it means. Are they destroyed? Have they undergone lysis or whatnot? No, it's not like that. So it is necrotic. It's just a title that needs to be identified better. Yeah, definitely. I agree. What I try to convey at this point is that development of mathematics at this point, starting from simpler, getting to more complicated, is a process where drags you into thinking that, yes, I am done again here, right? So we more or less understood what is happening, but yet again, it was proven not to be enough. Right? It was proven not to be enough because, of course, things do not grow as spheroids, right? For a gazillion of reasons. Another milestone model for me, it was the 96 paper by Galinsky and Galinsky, where in effect they were able to identify, and I would like to draw your attention to the gap between the tissue can be identified, the healthy tissue all around, like the green zone, versus the size of the tumor. So they were able to identify modeling-wise this gap. They were able to predict that in their model, right? And that was kind of an interesting and finally a space-dependent model. In this case, where it features two types of cells: cancer cells and healthy cells and acid, right? The assumption that they made was proliferation of the logistic, if you want, sense, as you can see there, and the part that I enjoy very much is that the diffusion is not the classical simple linear diffusion. It's not a delta that we quite typically write, right? Because the diffusivity, if you want, of one family N, right, depends on the other family in this particular model. So they were able in 96 to identify this characteristic which drives modern development of models. Fine. So they were able to do that. But again, this is away from identifying cancer islands. Right? So the community cancer islands, the ones we started to see in the beginning, concentrations, if you want. So
sorry, how
yes.
much in what sense do you reconstruct the previous picture? I mean, I don't understand.
Well, I don't have here their simulations, but what they are able to reproduce is in one dimension, they are able to reproduce the concentration of cancer cells dropping, the increase, if you want, of the concentration of the healthy tissue, and between them, something that looks like a gap. It's not void. The concentrations of the two communities, of the two colonies, is very low, and this, if you want, narrow margin moves with the growth of the tumor. And this is the effect, of course, of the acid. If you depends, of course, on the parameters, but if you have a look on the equations and how it works, it is the effect of the acid which, in effect, obeys a different equation effectively because of the linear diffusion. And it makes sense. It's a molecule, somehow diffuses faster. Okay, good. So, and then the community said, okay, let us put some more biology to understand what is happening. There are many more things more important or more equally as important, if you want, as the acidity. And somehow to drive my case today, I use the urokinase system that it is a multifaceted, if you want, plasmin, in effect, is a multifaceted protein, or the UPA is a multifaceted protein that, on one hand, prohibits, if you want, the migration of cells. On the other hand, participates by activating MMPs in the proteolysis of the master, of the extracellular matrix. The biology is interesting. The biology is complicated at this point, but what I want to draw your attention to is the complicated mathematics behind that. And this is a 2006 paper, celebrated 2006 paper that has drawn more than 1,000 citations. More than that, much more than that, for various reasons. Biology was one. The numerics that we are going to discuss in a moment was two. But another point, which I tried to touch upon in the beginning, is the logistic proliferation terms here, 1 minus C. At the time, we would understand the carrying capacity as a hard boundary for the concentration, i.e., in this non-dimensionalized version of the model, the community would understand that C is bounded from above by 1. And this is how it was communicated. Carrying capacity as a hard. Then, of course, the simulations came along, and they would exhibit clearly that there is an overshoot of the concentration C of the cancer cells above this hard boundary. And the question was raised, are the numerics any good? This gave rise to analytical investigations of the model, where analytically it was proven that indeed this is not a hard boundary, i.e., transiently in time, C can exceed this 1. Which for us, I mean,
But if that red term is there, clearly you're changing the carrying capacity, so.
everything is complicated. Yes,
Yeah.
the dynamics are very complicated. But the proof was not on the proofs were not on this model, which is quite complicated. They were simplified versions, right? But they exhibited in main case that the carrying capacity was exceeded by the concentration, i.e., it is not a hard volume exclusion term. The translation back in our understanding of the biology was wrong. And nowadays, the carrying capacity is used as what it can sustain, if you want, for longer times, the concentration, but it can be violated temporarily in time. Okay, good. So that was another point where lots of discussions came into the game, and this is when I started working on this field. And to make sure that we were able somehow to tackle this numerically, this problem to the extent of, back then at least, state of art of numerical methods for this type of cases, we did develop a second order in space and time, adaptive in space and time, and multi-D method that is what is called implicit explicit, right? And it is a combination of finite volumes and finite differences. So in effect, you write your system as the one before in kind of a vectorial form, like this one, right? And what you do then is you discretize that. What we did in this case, as I said, is the second order finite volume in space discretization. And this is how it looks: advection terms, diffusion terms, reaction terms, diffusion, reaction terms. And for you to solve that numerically, what we did was the implicit explicit coupling. So we said, wait a minute, diffusion is costly and not precise. That should be implicit. Reaction terms are stiff. Some of them should be here. Some of them should be on the explicit side. So we did develop a number of, if you want, variations of the model in order to be able to devise a proper method that could reproduce the dynamics to a high fidelity. Just for posterity, and since we did spend some time, this is how the dynamics for this system look like, the one that I presented before. The green line is the extracellular matrix, and the blue line represents the concentration of the cancer cells. These are the initial conditions: constant extracellular matrix, the green stuff, and an initial concentration of cancer cells, an initial spike. The dynamics as they are in the model lead to this wave that consumes the extracellular matrix. So this is the extracellular matrix is consumed, if you want, by the cancer cells. But of course, where I want to draw your attention is what happens on the rear, right? Because this is all the money, if you want. This is why all the fuss is all about. You can see that concentrations appear out of nowhere. Concentrations merge, they travel together. And of course, you would say that my numerics are wrong. And that's why the community started doing good numerics about that. It is highly sensitive numerically, but the numerics are not wrong. These are indeed the dynamics of the system. These are indeed the dynamics of the system.
Is that sort of a steady state that you reach at this point, or what?
No, it continues. These spikes come and disappear. So this continues. Of course, at the end of the day, you have to play with the boundary conditions, right? But until you have a problem with the boundary conditions, these dynamics continue. Is it? That's a good question. What is that? What is happening behind? I can tell you what it is not. What it is not, definitely, what it is not is what we were looking for, cancer islands. It is not cancer islands because the cancer islands, as we have seen in other experiments as well, are disconnected. Whereas what happens in here, all these rich dynamics that happen in here are behind the invasion. So the tumor has grown, and this is the intratumoral environment, which of course raises the question, what is the necrotic core? What is happening with all that we knew before? Well, I don't know, right? This is true.
Just because I don't recall the equations, like, is it, the extracellular matrix, then there is some nutrients?
It was the extracellular matrix, is this green stuff, and then there is a number of proteins that, well, in this particular case, but somehow the interactions are so complicated, which you cannot really tell that who is what. Yes. Logistic proliferation implying that there are some resources undescribed as such, as we typically do in these models, which of course raises the question, where do they come from?
Sorry, to follow up on that. So
Yes.
To explain the necrotic core, you would have needed that the resources are space dependent.
Yes,
But in your equation, that non-dimensionalized one
One.
was fixed.
yes,
So
right.
there's nothing in here that makes the I'm a little confused.
There is nothing here that makes the resources
Space dependent.
space dependent. They are limited, hence the logistic term, 1 minus C,
Right.
right? But they are not described but they are abundant regardless of space. So you have enough where you are, but limited. Yeah, in this sense. The point is that you don't get the dynamics that you were looking for, right? The formation of the islands.
So the blue things are already, so I'm a little confused.
That was one-dimensional thing. The two-dimensional simulation, and later on I have a better one.
So the point is that there's spikes, they're not in width, is that your concern? I'm not-
Well, right. They're not really spiked. We don't really know. So this is the two-dimensional thing. That's the propagating wave, as we've seen before. And the extracellular matrix is consumed, if you want. And this now is intratumoral. And what happens in this particular model, intratumoral, is this way of dynamics. In a later paper by Thomas, right, was it with Kevin Painter, you argued about chaos in an augmented version of the system. The chemotaxis, right? Okay, good. So still we don't have an answer, and that is somehow the problem. And when you do that, you go back to the biology and say, okay, what are we missing? And what we miss from the biology in order to understand was at the time, we believe that it was EMT, right? Epithelial, if you want, like cancer cells, which they due to EMT, they change their character, they enter the bloodstream, they exit somewhere else in the organism, secondary location, possibly they undergo the opposite transition, right? And they give rise again to metastatic tumor. The drivers of EMT are, of course, a big question that is about what starts the EMT, how it is driven, what kicks off the MET, what happens with transdifferentiation to cancer-associated fibroblast cells. So it is very complicated in any case, and we have heard discussion about that. In our case, we wanted to realize or not the introduction of a second system of cancer cells, a second family of cancer cells in the system would have been sufficient to create these concentrated islands, whether we would produce the concentrated islands. And for that reason, we did introduce migratory, if you want, mesenchymal-like cancer cells in our system, along with the epithelial-like ones. We introduced EMT, if you want, a cellular programming process in the system, for which I will give you a few more words, and to try to understand whether the cancer-associated fibroblasts were able to. We also had, the answer is no, we didn't succeed into finding islands, but this is what we tried at this point to do. So what was our EMT like? Our EMT-like was dependent on growth factors in the environment. Growth factors at this point, as many as you need, not infinitely many, but this is not a limiting factor in this particular manifestation, that they bound on the cancer cells, they get released of the cancer cells. If they are bound, a signaling process is triggered within the cells, which eventually drives them to possibly change their phenotype from epithelial to mesenchymal-like, right? Adjusting for time, because these processes are assumably much faster than the development of the tumor itself, so rescaling the proper time, right? We were able to simplify our, in this case, if you want, a simpler multi-scale model to be able to identify the dependence of the EMT process on, if you want, the growth factors in the environment. Now you prescribe the growth factors and you accordingly adjust the EMT. Sure. No, you go.
So there's no concept here of cell communication, like in notch delta signaling, which is known to be related to this conception.
No, only through, if you want, implicitly by the growth factors, which we know, for example, that TGF-beta is produced by cancer cells, it is picked up by other cancer cells, implicitly, if you want. But in our attempt to identify these cancer islands and be able to reproduce those, we build the model step by step in some sense. Okay, good. I will, now it will be a little bit faster. We were able somehow to see similar dynamics as before, right? We were able to see similar dynamics as before. The tumor grows. This is epithelial-like tumor in an environment. Gradually, it gives rise to mesenchymal cells. This is the red zone that you can see here. The mesenchymal cells break free from the initial tumor as they are more migratory. They exhibit the same, if you want, dynamical behavior as they extend in the tumor, and we are happy. But still, all these dynamics are inside, if you want, the tumor. It is not that we're able to produce something further away. Right? Sure.
Depends on these islands in time.
They grow, or depending, as they grow, they merge with each other. As they grow, they merge with each other, right? And they give rise to larger, more complicated islands. I can show you in a minute what we think it is. It is happening. Right. So still no joy, if you want. Okay, but still the dynamics build up. At this point, we started worrying about whether the models make sense in a mathematical realm. Because you start writing one equation after the other, you change this term, you put the other. You subtract, you add, you divide. After a while, your supervision, if you want, of the quality of the equations is in the tartars. So you have to do something better. So for this particular model, and based on previous works, I could mention Winkler, Yushantao, Marciniak, Ptasnik, and other people. Based on previous works that they are never directly applicable, right? We were able, at least in this particular case, to prove a global existence, uniqueness, positivity of the solutions. This costed for us 2 years of a priori estimates in order to do that. But we were certain at the end that this model makes sense also in the mathematical universe, which is something that I want to draw our attention again. As long as we haste, and we do well to haste into producing new models, testing them, we might neglect that what we produce might not make sense, mathematical sense. And if it doesn't make mathematical sense, nothing else matters, if you want, in some sense. Okay, good. Then I will not come to any details about that. I will skip through that and say, okay, look, let's go back to the drawing board once again. And going back to the drawing board, we made a realization that I think that I mentioned the first day. And the realization is the following. We do know that mesenchymal, stem-like, if you want, mesenchymal-like cancer cells exist in the system, right? But they come in much fewer numbers than the epithelial-like. The epithelial-like cancer cells are to the order of 10 to the 9. The numerics for that is feasible only if you do that in kind of a density, right? 10 to the 9, 10 to the 10. It is almost impossible to do that in the individual level. But the mesenchymal ones, They come in far smaller numbers, which you can tackle individually. So we said, okay, forget about the mesenchymal cells here of density, replace them. Replace them by your choice, if you want, I can tell you a little bit more what we chose, but your choice of individual cell description. In this case, currently we opt for, if you want, SD is for the migration of the mesenchymal cells, one equation per cell, with cell-cell interactions, cell-cell adhesions, are other works that we have seen these days. This is what happens at the individual level.
So this is SPD, yeah?
Yes. Oh, not it's SD. SD.
So you have
Yes, there is here the diffusivity. That's the drift. Sorry, that's the drift, and here's the diffusivity. And what we advertise.
It's not Brownian motion.
It's not Brownian motion, exactly. What we advertise, I will tell you why we don't. What we advertise, what we believe it's more biologically appropriate. It is a compound Poisson. This is what we believe it is more biologically correct than a Brownian one. And the reason for that is the nature of white noise and Brownian. Yeah, sure. Again, this is just, if you want, a first manifestation of the hybrid model that we advertise. There are interactions not seen in this equation between the cells. And what I want to say a little bit more is that we maintain EMT and MET transition between the two families, i.e., and this is the hybridicity. We have a system of densities, that's what you have there. And then you have individual cells, that's what you have there. And there are transitions from one to the other, according to the EMT. So you have densities and individual cells, and how do we at least couple those? How we do that, right? And what we do is schematically, if you want, represented by that. The idea behind our thought is the following. Look, the integral of the density is the mass. Fine. So if I assume that one cell is square, just for the fun of it, to make things simpler, it's not a square, but for the fun of it. If I assume that in this squarish location, if you want, that it is the size of one individual cell, EMT takes place, then this corresponding density needs to be materialized. And we do the materialization of densities to individual cells with two operators, back and forth, right? From one, if you want, description to the other. The operators can be driven by EMT or MET, but what we propose here could be even more general. And this is how we work that through.
Compound Poisson.
Yes.
So would it be like Poisson sum
Yes.
of Bernoulli one plus one and negative one, not like or not?
No, we don't, not negative one, 0, 1, 0, 1. But compound Poisson of what we compound,
So it's compound.
sum of Poisson events, if you want. Poisson distribution for each potential event and a sum of that.
I think that it's Poisson sum of Bernoulli.
Yes. Or no, sum of Poisson distributions. So,
So you're saying this is Poisson sum, or it's actually it's called lemon type A distribution. Yes.
possibly.
Actually,
I would abide to your expertise on this point. Yes, we describe that as compound Poisson to describe that there are Poisson-driven events more than one, possibly, but certainly not a Brownian. This is what we somehow don't like. We don't have strong evidence. Anyway, so how do we do the coupling? In effect, it is easier described, if you want, at the discrete level. What we do is we do a strong operator splitting approach. In effect, we consider the densities and the individual cells separately. And the strong splitting says the following: forget about the interactions and the reactions between them, just consider migration, advection, diffusion, and do that. And then freeze time, if you want, and as you freeze time, consider all the reactions between them. And then perform the other half of the migration. And this gives rise to a strong splitting type of approach that allows us somehow to couple numerically, but also analytically, here numerically, to couple the two families. And it is, since it is computationally not expensive at this point. And the reason it is not expensive That is totally inhumane. No, I'm doing good. I'm doing good. Let me show you how it works somehow let me show you how it works to start having more of a feeling of what we suggest. The gray thing represents, if you want, the healthy tissue that we saw in the beginning. And this is meant to be kind of, if you want, an invasion assay of some sort. What you see as through the ISO lines, these are ISO lines, is the concentration of the epithelial-like cancer cells. So it is a snapshot of the tumor, if you want. What you cannot see in this simulation is the mesenchymal cells, which they invade in the tissue, and at some point they undergo MET, and they start proliferating, giving rise to these independent islands, which as they grow, they merge with each other. What is nice about that is that the overall growth rate of the tumor with this approach is much faster than the invasion growth through simply invasion, because of course, proliferation happening in many islands leads to exponentially faster overall growth of the tumor, rather than proliferation happening only on one island. Being Greek, I like islands.
What could cause stopping the merging?
Stopping the merging.
They're growing.
Sorry?
growing.
In the figure, in the
Exactly.
initial tumor that you
Keep them
showed.
Yes, this is what I suggested in the beginning, that what we see is a snapshot of very different times, small islands and big islands. And when you harvest the liver and you take a slice, it is as if you have taken one time instance of that.
Yeah.
Does that answer your question, first of all?
Yes, I guess you're trying to say that long term, everything would have merged. You're just taking a slice at some previous
Yes.
points.
And this is what
Just that.
And this is what I believe, that if the liver could be, that we saw in the beginning, could be in kind of a lab, continue this process, the islands would have merged. Because the islands that you see there, and this is, I think, the key point, are of different sizes. But I didn't understand exactly what you mean, freeze it.
Suppose you had a way to unlock that merging.
Yes,
So you have a tumor with islands,
yes,
but you put a stop there
yes.
to the process. In that case,
Mathematically, it would mean that we should stop the proliferation. If this is what you mean mathematically, or?
there are situations in nature
Mm.
where islands like this are generated. But in that case, they keep separated. So maybe we can.
And they keep growing, and they keep growing.
They're going in height.
They go, okay,
going
they,
in
yes,
waves,
exactly.
okay?
Respect, yes,
This is-
agree.
There is a model explaining something called cause in England or somewhere that was generated, but if those spores are separate
Mhm.
forever,
I see,
you can visit there as a tourist.
I see. Okay, as I promised, I will be much faster. The same we can do here, to prove my case. We can do that also in 3D. This now time, it is very coarse numerically, one manifestation of the individual cells as they undergo in the same tissue, EMT and MET, which of course, it is a question, which tissue? Head and neck squamous carcinoma cells could do that in the same tissue, but this is not something that generic. Still, this is for the development side of things, okay? Whether it is just in one tissue or not, it is something that you can build in the system. Since the chair will be, since the whisk, I will skip this particular part. Just a quick mention. No, I will skip it completely. Just because it was a question before previously. This is what we use for parameter estimation. stochastic ESS, and we have found a very robust MIGO implementation of this. This is for parameter estimation in open domain, right? This is what we opt for, parameters. What we have used a few times and it has worked thus far. But again, let me skip through to what we currently do and what we want to do. What we currently do is we have developed a first rudimentary network connecting different box organs. Organ 1, organ 2, organ 3, organ 4. The connection between them for the moment in this particular work that we have done here is very rudimentary. Again, you could have MET if you wish on the same tissue, but you can, through your network, circulatory or lymphatic network, you can extend that. And you can even have a good control, and I will show you in a minute. You can even have a good control on what is happening, how it happens. Good control means the following in this case. There you go. Good control means the following. In this case, in spheroids, how to make that computationally faster. The previous simulation that you saw, it was half an hour, more or less, because it is completely parallelizable, the different organs, right? And we can go to a larger number of organs, which we can, with a more elaborate, and in this case, we identify what organ is what, how they are connected downstream, and whether or not there is circulation of circulatory tumor cells after they enter the bloodstream, whether or not they can emerge in the same organ later on. So we have a control on that. What we don't control yet here is the actual blood flow. Right, so what we control here is the average speed with which cells move from organ A to organ B, right? But that, for the moment, has given us a very nice control on the overall landscape of metastasis. We are based on a previous, on a work of statistics. This is what you see here, in effect, on, I think, 2,000 patients, first diagnosis in a number of organs, and secondary sites that they were later on identified. And the authors organized this information with probabilities. If, in effect, head and neck cancer was the primary tumor, these are the probabilities in all these 16 networks. And we have entered this process of, in our case, what you have seen before, the primary organ being melanoma, if the skin, if you want, and what our model parameter estimation, so that our model predicts the probability of spreading to secondary organs. And we have done that with all the collection of primary. So in effect, we have a huge metastasis matrix that we have the probability. What probability? I should be clear. Probability of cells, individual cells, from primary organ, giving rise to secondary locations, right? This is what we have identified, so that the statistics over the population of 5,000 people is similar to what has been experimentally measured.
Sorry, in your mathematical model, the different cancers, how will they get reflected in the mathematical model in this step?
With, well, right.
Specific parameters change and how do you those?
Right, it is the connectivity, if you want, of the network of these 15, 16 different organs, the time that, average speed and time that the cells, individual cells need from this organ to that organ, according to who is who, right? And these are parameters within our system.
How do you pick those parameters in your model and so on?
We pick our parameters in the model, right, with a parameter estimation, of course, approach that aims to, at the level of society, 2,000 patients, reproduce these dynamics.
So you fit that data.
We fit that data, but we identify parameters at the level of the cell, and we fit the data at the level of 2,000 patients. Yes, 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 right. And of course, the biggest difficulty at this point is, of course, that the only validation that we can do, because we don't have individual patient data, we have collective probability data, is we validate with subtracting, let's say, one of the organs, developing the parameters for the rest, and then identifying.
And that works quite well. You get,
More or less, we are, as I said, this is current development.
okay.
Yes, please. Sorry, I can't hear you. Yes. And that was developed in identified in this particular. What is wrong with this work of ours is that these are from a hospital, Charité in Berlin data, where the patients were not let untreated. So there is treatment here built in, which has polluted our parameters. But we don't aim at this point that we can, what we aim is that we develop a framework to be able to do these things. Yes, please.
So from my understanding, the different organs, all of the other parameters, so penetrations and other aspects, they remain the same.
No, they are not.
You adjust the parameters.
We adjust also those, and one of
A huge number.
there are many parameters. What we adjust is, as I said, the average speed and probability of extravasation in the corresponding organ, the proliferation on this particular organ, and what we like mostly, and I have not addressed, is the dormancy.
Yes.
The dormancy we have calibrated from a different work, which of course I don't have the time because the chair will throw chairs at me. Yes, in a moment. So. Yeah. Okay, I will finish now with what we currently do. We don't like box organs. We like real organs, and this is a brain of a healthy individual, which we use in our PDs to develop. And this is a work that we have done 2-3 years now, where the tumors, in this case, a glioma growing in the tissue of the brain by accounting for the geometry of the tissue, acidity, and a number of other factors. So our aim is to replace all these 15 organs from the box representation and the not so detailed physiological conformation to something more realistic, right? So we look now into lung and tissue, skin, right? To make that, to calibrate that as much as we can. And we emerge all of this information into AER, we would like that to be. For the moment, it is a VR environment where this is just a snapshot, but just to show you what you can do. I mean, in your VR environment, right? Maybe I should have brought here you can do 2 things. First of all, have fun by looking into, your simulations in almost real time. So the simulations take place in the desktop, and through 5G, they come into our visor. Our visors are not the newest generation, they're a bit slow, but it works. So they're almost, what you can get though, and what we care most about is measurements. So you can, we have a student that works on the computational interface where you can set a point here and a point there, and you take measurements in real time. And all that somehow is under development. And of course, you can imagine it's something that we cannot do just in academic environment, because you cannot risk your PhD student's career with an idea that doesn't work. And for that reason, we have decided to commercialize, not in effect to sell, because we don't have anything to sell for the moment. What we have for the moment is a pitch that has given us £250,000 for a company which is called Radical Health, and yeah, it's coming. It's coming. With that, I want to thank all of you, and of course the colleagues and friends online, and thank the chair for their patience today. Thank you very much.